Okay, going to do a quick video over Venus. Be two parts to the unit test, Venus and Mars. This is just the first video of Venus. So let's get going. Venus is, because its proximity to the Sun, is only, or is best seen first 3 hours before sunrise and 3 hours after it sets. It's oftentimes referred to as the morning and evening star, despite the fact that it's a star. It just happens to be bright. Third brightest object in the sky, actually, behind the moon and the sun. It's very reflective due to the fact that it has sulfuric acid clouds in its atmosphere. These clouds cover the entire atmosphere, and these have a kind of a yellowish hue, which makes them have a really high albedo and therefore reflect a lot of light. Therefore, the planet is very bright to humans on Earth. It's most visible in the superior conjunction, which is on the which means it's one that's on the other side of the Sun from Earth. If you look at this picture, it's most visible over here if Earth is here, and then it's least visible here because it's almost like the new phase and the full phase of the Moon. If you remember back to those units. Physical properties of it, it's almost exactly the same size as Earth. It's a little bit smaller. It's got a little bit less mass. Would have very similar gravity because the density of it, mass over volume, would be very similar to Earth. Would be the most easy to adjust planet, I guess what you would say, gravitationally, if you could stand on it. It also has no moon. One of two terrestrial planets has no moon, Mercury being the other. Rotates weird. We call it retrogradely. Rotates clockwise, whereas all the other planets rotate counterclockwise. The Sun rotates counterclockwise, and you see in this image here, all the planets of the solar system rotate or orbit in this way. So they orbit and rotate in the same direction, except for Venus. Venus rotates in a backwards motion relative to all the other planets. Probably got hit by something. Again, it's a theory, but it just doesn't make sense with all the other planets forming. The idea of uniformitarianism. All the other planets form at the exact same time. It should basically be rotating the exact same direction as well as orbiting. It does orbit in the same direction as the rest of the planets. Has an orbital period of 225 Earth days. Because it rotates so slowly, it has no magnetosphere, or very little magnetosphere. We'll talk about that. Hard to see the planet except for that it's cloudy. This is a visual shot of Venus with a pretty decent telescope. It's really just kind of blurry because all the light that you're seeing is just being reflected off of the clouds. I actually didn't know its rotational rate until the 60s when Arecibo calculated the rotational rate using microwave, which is exactly how they calculated the rotational rate of Mercury, if you remember. That's just a picture of Arecibo as a reminder. You look at another types of light, it looks kind of Earth-like. This is in the ultraviolet. Looks blue and white. That's obviously misleading because we don't see things in the ultraviolet. But early scientists believed it was only about 10 or 20 degrees hotter than Earth. They knew it was closer to the sun. They knew that it had a CO2 atmosphere, and they've known that CO2 is a greenhouse gas for some time and would retain some heat. Now, they did not realize that it had as much CO2 as it does, but Arecibo detected it was much, much, much hotter than what previously was thought, and around 900 degrees Fahrenheit. Mapping of the planet's been done by the U.S. Several different occasions. First time was one of the Pioneer probes mapped it using radar graphs or what's essentially sonar to kind of give a topographical map. This is in the left here. This is in the 60s, late 60s, early 70s. So that's pretty good for that time. We're definitely able to point out some major features in the north and the southern hemispheres. But in the 90s, we sent a new probe called the Magellan probe, and it mapped it much, much more accurately. Again, topographical because it's shooting through the clouds, the radar. And that's because radar is a longer wavelength of light and it can penetrate the clouds. Russia's the only country that has ever landed a probe on Venus, giving us the only pictures of the surface of it, some video of it. Also gave us very detailed atmospheric data, very, very big contributor to our Venus knowledge. That country, Russia. Venus does not have any signs of plate tectonics. Remember in class I kind of blew these two images up and you can kind of see the tectonic plate ridges and stuff here on the planet Earth. If you look at it, that's Earth with a radar graph. If you look at Venus with a radar graph, you don't see any of those things that are telltale signs of plate tectonics like ridges or plate boundaries. We just don't see those. Venus has two large, what we kind of call like continental areas. One in the northern hemisphere and one in the southern. And the one in the northern is called the Ishtar Terra. Ishtar is the Babylonian goddess of love. It contains a couple of notable features: the Maxwell Montes, which is the largest mountain on Venus, and the Cleopatra impact crater, which is a very large impact crater on the Ishtar Terra. So if you can see, here's Maxwell Montes. That's the Cleopatra crater there. In the southern hemisphere, we have another large continental-like area that we call the Aphrodite Terra. And it's named after the Greek goddess of love. Venus, of course, is typically named after women in history or goddesses. There are a few man names on it, but not many. So the Aphrodite Terra is just a larger region in the southern hemisphere. Venus has three different types of volcanic features. The smallest of them are what we refer to as lava domes. Lava domes are the idea that that magma breaks through the surface of the crust, kind of bubbles up, and then that magma recedes back into the mantle, and it kind of leaves this shell of what would have been a volcano, but it gets crushed down by the atmospheric pressure. So we'll flip to a picture of that real quick. This is kind of what it looks like. It looks kind of like cookies when you have them in the oven, and when you take them out, they kind of deflate, kind of shrink down, if you will. If you take out the cookies a little bit too early and they're kind of all bubbled up still, and if you leave them, they'll kind of just fall like a cake would fall. Kind of implodes, if you will. Second type are shield volcanoes. Lots of shield volcanoes on Venus. These are the type of volcano that forms over a hot spot, which is a rip in the mantle. This is much like the Hawaiian island chain, which we spoke about in the Earth unit. These are very, very numerous on Venus. The largest of the volcanic feature are what we identify as corona or coronae. And these are just what I call super duper mega volcanoes. They're just ridiculously large. They are larger than like the state of Texas, some of them. And it's almost like the book kind of defines them as a circular plateau. So I'll show you a picture of one here. It's a really large region. Here's a 500 kilometer scale, right? That's quite the distance there. And a kind of spot along the sides of these things, little smaller breaks in the mantle, will cause these other volcanoes to pop up. Now, how do we know there's volcanism on Venus? We can't see it in the visible because we can't really see through the clouds. The only reason that we really believe that Venus is still actively erupting is because SO2 or sulfur dioxide amounts in the atmosphere, which are spewed out in large amounts in volcanic explosions on our planet, and we would assume they would as well on Venus. We see fluctuations in these amounts in the atmospheres. So sometimes we'll see large amounts of SO2, and some other times we'll see not very much, and then it'll just kind of go up again. And related to that, we'll also notice lots of lightning, and lightning is associated with volcanic eruptions here because of the static friction that the particulate matter in the volcanoes erupt out. And this is an actual picture of a lightning strike in a volcano on Earth. So we'll notice again these lightning discharges will kind of uptick with these SO2 amounts increasing. Impact cratering on Venus. There's not a ton of impact craters on Venus because it's believed to be so volcanic that these things are getting filled in with magma. It does have some. There's just not a large proportion of them, and it's much like Earth. I mean, Earth has some, but there's not many of them. Earth has them basically erased for different reasons because we have plate tectonics that kind of erases them, or we also have erosional factors. But of course, Venus would probably have some erosional factors from acid rain or something like that. But also the magma being basically resurfacing the entire planet about 500 million years ago. Most of the planet, anyway. And a lot of the meteorites burn up. It has a very large, thick atmosphere, so this causes a lot of them to burn up, just like in Earth's atmosphere. These are some actual pictures of Venus from the Venera probes, thanks to Russia. Its atmosphere is dense. It is about 90 times the pressure of Earth's. Most people compare it to the bottom of the ocean. If you just kind of jump out of a submarine in the bottom of the ocean, atmosphere is about 90% that of Earth's. It would crush a person flat. I mean, basically implode them. It would be a disgusting way to end it. If you could somehow miraculously survive the high temperatures. Atmosphere is almost entirely CO2, and that's the reason that the atmospheric pressure is so much. This is a heavier molecule than what we have. Most of our atmosphere is nitrogen, which is a much lighter molecule. Atmosphere has these sulfuric acid clouds in it. Probably again going back to the volcanic explosions or eruptions, because it erupting with SO2 or sulfur dioxide. And it's probably where these large amounts of sulfuric acid clouds come from. It gives Venus this yellowish hue. It kind of traps the greenhouse gases below in the troposphere, and any gases above are basically ionized from the solar wind because it has no magnetosphere, or little magnetosphere. So the greenhouse effect that it works, or how it works with Venus, is basically the idea that because the atmosphere is thick and it's mostly CO2, all the energy that is allowed to penetrate doesn't really escape. So it just kind of keeps getting hotter and hotter and hotter and hotter. But only about 30% of that radiation does get in because the sulfuric acid clouds are yellow and therefore high albedo, and they reflect a lot of it. So a lot of it is just reflected back, but any that does actually penetrate in absorbs into the ground, then it'll reemit and kind of bounce off and back and forth between the clouds and the ground, and much like a blanket on a person. So because it has this slow rotation of negative 243 days, it just is not rotating fast enough to have a strong magnetosphere. So it's a very weak magnetosphere. Anything, again, above the sulfuric acid clouds are completely ionized by the solar wind. It just kind of rips off most of the stuff. But anything below it, for some reason, the sulfuric acid clouds protect those greenhouse gases below it. And that's really where the heat of the planet comes up. remember, for a strong magnetosphere, it needs to be not only geologically active, but it also needs to be rotating rapidly. So if you can see this temperature swing here, right? Up here it's not that bad, and then you get down here, this is kind of gets crazy, right? This is really, really, really hot. And that's because all the CO2 and stuff is down here, and all that radiation just keeps bouncing back and forth. So, all right, well, that's pretty much it for Venus. I hope you enjoyed the quick review, and I'll catch you in class.